morning. Hello, everyone. I just finished the scoring for your midterm. Maybe tomorrow I will give it to you. There are some notes that you need to be taken on from the midterm because I think one or two questions may be a little bit confusing, so I'm trying my best to just adding some points to your score. Okay. So today's course will be continuing and completing the chapter 13, and I think we can go to the introduction of chapter 14, which is the partial derivatives. So last time we get the arc length and the curvature, right? So what we are going to complete now is there are other terms in the vector functions, the other vectors terms, that is which we call the normal vectors and the binormal vectors. Okay. So normal and binormal vectors. And then the definition for the normal vectors. So normal vectors we called vector n, or simply unit normal. This is defined by the unit tangent vector derivative defined by its magnitude value. Okay, so this is suppose that we are having a tangent, a unit tangent vector, the t. We know that the t prime, let me write here, the t prime is going to be 0, which is an indication that the angle will be 90 degrees, right? So as a notes, let me add some here. Then we can get the unit tangent vector from the vector position itself. We derive and then divide by its magnitude value. If you remember how the directions within these two vectors, so this t, if you remember, this is going to be pointing the direction of increasing parameter t, right? And this n is pointing inwards towards the concave part of curve, which means that if you look at the graph on the left side, if we increase t and we get the sense of the direction of the vectors, the unit tangent vector is pointing the direction of the increasing t. So for example, if this is going to be our graph, or let me just draw a graph again here. So if this is the curve, the unit tangent vector is precisely as following the same directions. Okay. And meanwhile, the normal vector, because we define the normal vector as the derivative of the unit tangent vector, which is orthogonal, then we can have that for every t, and suppose that this is going to be the concave part So the normal factor is going to be inwards, so that way, and orthogonal to t. So this will be the n. Okay. It's the same as the picture on the left. Okay. If we look at the picture on the left, it's completely giving you three vectors, t, n, and b. Okay. And based on what we have here, the binormal factors, we can say, is the cross product from the t and cross n. So we can we say that because by definition the binormal is the factors orthogonal to both t and the n. So basically, if you are asked to find the normal factors or the binormal factors, the first thing you need to do is finding the unit tangent factor. Okay, finding the unit tangent factor, and then derive, find the normal, and then take the cross product, okay, for the binormal. Okay. So yeah, as simple as that. Okay. So you just plug into the formulations. So all these factors, the normal and binormal, they are depends on the direction of t. And you can also see if we move out the segments, we change the t, and the normal and binormal also change, okay, based on their own definitions. Okay. So the normal will be orthogonal to t, and the b will be a product from the t cross n. And between these factors, we have three factors, right? So t, n, and b. So between t and n, it seems that we have some kind of plane that we can draw from that two factors. And from the n and b, we can also have another plane. So that is, we call the normal plane and osculating plane. Okay, we are going to see later on. Okay. Okay. Now this is what we have in between vectors. So we can some sort of a drawing a plane out of these three vectors. So we call this osculating plane for the vector t and factor n, and the normal plane for the factor b and factor n. This is determine t and n, right? The osculating plane, and the normal plane is determine by n and b. Okay, now if you look at the osculating plane, the plane is actually, they are somewhat in line with the curve itself, right? So the osculating plane that is closest to contain the curve near point B, and based on its own terms, the osculating comes from the Latin words osculum, which means kissing, which means it's going to be closest to the curve. Okay. So a plane that contains the curve itself. And between this, the osculating plane, within this osculating plane, if you remember, this is the curve, okay? So if this point, let's say the point is here, remember that we can find out the curvature, right, within this curve. And from what we have before, we can somehow drawing how the curvature will be. Let's say just illustration, maybe the curvatures are here, and we can draw the curvature like a circle, okay? Which we have the radius, the circle is 1 over curvature, right? So the radius is 1 over curvature. And this is what we call the osculating circle. In all these terms, the osculating plane, the normal plane, the osculating circle is, I think, helping us to describe, okay, how the curve will be. Because I think if you are dealing with, I think later on, some sort of modelings or simulations that may be having some complicated curves, and you want to analyze how it looks like, this is some tools that we can analyze and observe. Okay? Okay, so if we take into some random curve and try to moving out the point P, like for example this one here, we can see the curvature is changing, and you see the circle is also changed. So when the curvature is large, the radius will be small, right? Because of the 1 over curvature, okay? Because of this, so radius high, then curvature it will be low, okay? Because r is 1 over curvature. This is we call the oscillating circle. Circle in oscillating plane that pass through P. I said P is the point that we move from the curve with radius is equal 1 over curvature. And center distance 1 over curvature from P along the factor n. So this is just to say that the factor n will go through the center of the circle, as you see from the picture. Okay. So, and the circle, this oscillating circle is, I think, one of the tools to see how the curvature will change. Okay, how to see where the largest curvature takes place, which is on, I think in this 2-dimension graphs, it's on when the slope is changed from positive to negative or from negative to positive. That will be the largest curvature, in which we see the circle is really small. Okay. And when it's moving out from the horizontal tangent, right, the horizontal gradient, we see the circle becomes large, right? Okay, and then we are going to see the last section within this chapter 13, which is the torsion. Okay, let me write summary for all the formula that we have. Okay, so first is the unit tangent factor. This is r prime. And the normal factor. And the binomial, the t cross n. And then remember that we have the curvature. That's by the definition is dt over ds. And then we can rewrite this and take into and we can also rewrite this in terms of cross product r prime cross r double prime and then divide by the magnitude with power of 3. So far this is what we have. Okay. Okay, just to note that from the last part here, if you remember what we did in the curvature, so for parabola y equal x squared, we see that in our calculation before that curvature at point 0 is 2, so here, so which means the radius of the circle is 1 over curvature, so this will be 1 over 2. Okay, so if we take, so let's say this is our point P, okay, and this is our normal vector, okay, and this is going to be, let's say this is the T. So the N will be 0, 1 vector, And this will lead us to this 0 point, so center of circle is 0.5. And from here we can write down the circle formula, which is the circle is graph on the left side. Okay, this is just just to note when we have the parabola and we can find the curvature, then we can also graph the circle. So next is the torsion. So if we see this picture here, okay, remember that the curvature is dt over ds, right? The change on the tangent vector with respect to the length, the arc length, right? So as long as if we move this point P, which means that the tangent vector will also change, right? So we are going to see that the curvature will indicate how the curve will bend, okay, will bend. Okay. And also, this curvature also indicating how the normal plane changing, okay. So this is the normal plane, this is normal plane. So if we change the point, let's say we move the point goes through here, okay, maybe if we take this one here, P is here, then perhaps this is the T, and maybe the normal plane may be a little bit changed, okay, maybe a little bit changed, but it's not really good. So let me write here, P change, when P moves along C, dt ds indicates how the normal plane change. And also the vector is parallel, so dt ds, we can say it is parallel to vector n. So and when we move the point P, the tangent vector is also rotates, right, with the direction of the normal, right? Okay. And since B is the normal to the osculating plane, then if we take the dB ds, let me write here, so dB ds, then indicates how the osculating plane change, okay? Change as we move P, okay? And then dB ds is parallel to the end, right? So we can say In other words, in factor, if two factors parallel, then the difference between those two are just scalar multiplications, right? So we can have a scalar, and let's rename the scalar as tau. So tau is a scalar. And then if we take the dot product for n, so n dot n, so assume that n dot n is equal 1. Then then tau, or this is what we call the torsion, is the negative dot n. But it's still a little bit not easy to compute because of dBds. So we can exchange dBds with chain rule. So while taking the derivative of the dt, so we take, and ds over dt is basically the derivative of the factor positions, the arc length. So we can take the arc length as the magnitude value, right? Remember the arc length is going to have the integrations, okay, so integration of ds dt, right? So this is dBds. So we can write the torsion dot n over so this is the torsion. So torsion, maybe the best way to describe the visualizations is how the curve is twisted. Okay. Is twisting at certain point P. Okay. there are another terms for the torsion under the formula. It's quite long. Okay, so that's it for the vector function. So we are finished chapter 13. So we skip the motion. I don't think we are going to have enough time for that one. So we directly go to chapter 14. Okay, I think we can move to next sections. So this will be in the introductions to the partial derivatives. As you may see from this picture, so this will be a partial derivative. So we start from the beginning, the function of several variables. And I will go very quick in these introductions. So basically what we are going to do is we are going to see a function that is made up from two variables or more. Okay, so we start from, let's say, two variables x, y as our variable. Okay, so which means that the function is a typical function x, y. Okay? So we are going to input two variable, and then I think the best way to describe this is if we have three dimensions, like we have three axes, and it's just saying that if we put a point, xy point, then we will go through this fxy, which is in the z-axis. Okay, I think that's the best way to describe. So we can have a domain within the xy plane, and the range will be in terms of the z. Okay. So we can write maybe just as introductions. So function, let's start with function of two variables, meaning we assigning to each ordered pair from the real number xy in a set of domain and its range is set of values that f xy takes, which is maybe better write like the pair xy in okay, let's continue. Okay, so this is an introductions, function of two variables. And then if we are going to describe this, best to describe in 3 dimensions, and then we can rewrite the points based on the points becomes x, y, and z. Z becomes the function itself. You get the result of the x, y. So we can describe within this graph, and then we can describe that this is our domain. So when we put x, y within this plane, this will be the result, and we have the x, y, f, x, y. Okay, so this is just basically saying that we can describe as a graph. So this is a graph that is showing you set of all points x, y, z in the space curve, such that the z is equal to function x, y. Okay. And basically, if we are having this kind of graphs, we can describe in a 3-dimension curve or in 3-dimension shape, like we did before in the quadratic surface. Well, we are going to have a similar shape. Okay. Then we could adjust and we could arrange the shape based on these two variables. So we could arrange something like this. This is just showing you how we describe the curves. I think you can also check some of the graphing calculators. I think website like GeoGebra, they also can describe the 3 dimensions. I think you need to change the perspective from the classic 2 dimensions to adding one more axis, and you can describe the shape. So what's the deal within this shape? Okay. Now we can see that if we are looking at the whole or the general shape from these all pictures, we can see that at some certain points, we can see that they are, for example, this point here, this 2 point there, this 2 point, and then this 4 points. It has some certain different height, right? Which means that if we describe, like for example, like how we describe Earth, like we have the mountains and so on and so forth. So we can describe the contour easily within this function of 2 variables. Okay, so we can describe the contour. So contour mapping, and describing the level curves, because you have different height now, which is the z, right, in terms of the function xy. So we can describe the level curves by taking the function and taking to some constant. So we can project some of the mapping, the contour and mapping, in some models in a function of 2 variables. We modeled the position, which is xy, and then we equal into some constant to describe the height. Something like this, okay? So we can trace from the map. Okay, we can trace how it looks like, and sometimes if you see some maps, if you open the Atlas or looking at the Google Maps, I think sometimes you can change the view and you can see how the level curve will take different colors. Okay, will take the different colors. That is something also you could have done using these models. Another interesting feature is I think the humidity, the temperature. They are actually, because they can be adjusted by the positions, so we can get the maps, and then maybe we can take the average of the temperature, the humidity, and they are also modeled by the function of 2 variables. Okay, I think that's just for the intro. Okay. Okay, so this will be our calculus part. Okay. So limit. With limits and continuity. Okay, before we done here, let me put these 2 down first. Okay, let me describe first, and let me just take some quick review, okay, just to get the idea of what we are going to do. So we take the limit. Like for example, if we take the original limit like we did in calculus 1, so we take, let's say, some certain point x0, y0. We say that we take the limit as x approaching the x0, but we are going to define, like usual in calculus 1, we define, let's say, the x0 from the right, and we say that the limit exists because the left hand limit equal the right hand limit. Okay. And then this equal to some value of L. Let's say the L is here. And now, if we have 3 dimensions, so we are in the XYZ axis. Let's define the variables. Let's say we have x0 there, y0 here, and we have the domain is about that point. Then we are going to have some sort of a point here, and if we did it for all the sum of the domain, then we are going to have some sort of shape on the top like this. Okay. So this is the x0, y0, 0. Here is x0, y0, z, let's say z0, okay, or fxy. And we call this shape as a function of xy. So if we try to take the limit and approaching this xy, okay, approaching to x0, y0 of this function fxy, how we are going to do it? So in original calculus, we can approach from the left, from the right. Okay. Now we have here, this is the domain. How we approach this point here? Or we approach this point here, okay? That's the function. So here, from here, so we can have many ways. We can have many ways to approach the point, right? So we say, let me write first as a note. So there are infinitely many curves that can approach okay. Let me give you a quick example, okay, before we define all this. Let me give you a quick example before we did the definitions. So let's say we have an fxy. Let's say we have a negative xy divided by x squared plus y squared. So first we can try some numbers. We can try some numbers. and see whether we can have and prove that all limit within all the numbers can exist. So there are several ways. So first, we could take assumptions that the limit will be along the x-axis, which means we are going to take y will be 0. So we can take 0, 0 as our basic approach to help us proving whether this limit can be exist or not. So proving limit as xy approach 0, 0. Okay. Since we assume that this limit will be along this x-axis, so we are going to take 0 for y first, and we are going to see that this will be 0, x squared, and 0. So 0 over x squared. This will be 0, okay? Well, maybe before this, you can try to change all this to 0, and this will be 0 over 0, which is, we need to define again because it's not determinate, right? But then we are not going to use the L'Hopital rule because of this is not the same as we did in calculus 1, right? And then this is x-axis, and then we can also take the limit along y-axis because we can have many ways. We can have many ways, but we need to take some restriction to help us to narrow our conclusion. Okay? So the second assumption that we can take, we take the limit along the y-axis, which is x going to be 0. Or maybe this will be make you confused here. Maybe let me explain here what this is going to be 0 over x squared plus 0. So 0. Okay. So instead of exchanging 0, 0 directly, we take the assumption first and then put 0 first before we put all the constant. So we take the limit, approach 0, 0. So negative xy. And now this is going to be 0. Now 0 plus y squared, which is again, it's 0. So it seems we get the same conclusions. But we can also take another approach that usually will work for most of the cases. So limit along the x-axis, limit along the y-axis, and then the third one, we can take limit along, let's say y equal x, okay? So all this x-axis, y-axis, y equal x is just our assumptions because we can have many ways or many curves that can approach. But this is something that is easy to see if we exchange the y equals 0, x equals 0, and y equals x. I think that will be a very simplified curves to see. Okay, so if we take the limit, we are going to exchange y to x or x to y. So let's just exchange y to x. So negative x squared. This will be x squared plus x squared. And since y is equal x, we can say limit becomes x approaching 0. And now we see that this limit become negative x squared over 2x squared, and this is negative 1 over 2, which is not equal to 0, right? Let me put this into here. So probably the limit is not exist. So this draw conclusions that we need to prove that for every path that we can take, we need to prove that all the paths will prove that this limit should be exist. Okay. I think you can exchange the curve with any curve you can think. If the curve can help you to compute the limit, okay. Well, you can check the curve. Maybe you can exchange the curve with y equal x squared or y equal square root of x, or with any curve you can think of. Okay. That can help you to compute easily the limit. Okay. If the curve maybe making the things difficult, then I think don't use it. Okay, with these three simple curve, like y equals 0, x equals 0, y equals x, those three can prove, at least for y equals x, is proof that perhaps this is not exist. Okay, this limit is not exist. So let me describe in the definitions here. So if we have the two variable functions, which we have some domain, okay, and the domain is let's say close to some point that is described as AB, and then we say the limit of the function of two variables xy as xy approach this AB. Okay. We can write limit xy and b of xy equal to L. Okay. Like for example, if we change the approach for this one here, for this example here, let's say we change to, let's say the limit is taking to, let's say 2, 1 or 1, 2, let's say this is 2, 1. Then we can have precisely some numbers here, which is, this is negative 2 over 5. So the limit exists if we approach to 1. But if we approach to 0, we have some problem, right? The limit is probably not exist if we approach to 0. So first you can check the AB. If it's getting some result L, then I think we can stop and then, okay, limit exists. And then this is for the delta epsilon definitions based on limit. We still have this one here, but I was just showing you how the relations. Okay. So the epsilon is as usual. This is going to be within this L. Okay, so L plus epsilon minus epsilon, okay, which means that this is going to have some range here. That still we can say that if the absolute is really small, we say that this is going to have some value. Okay? And we can say the limit exists. And the delta is here. Okay. So here limit exists as xy approaching to 1. But when we approach 0, 0, it doesn't exist. Okay, so this is how we try to find different paths to approach the A, B. So we could make up our curves. We can simplify to help conclude whether the limit exists or not. So we say if fxy approaching L1 as xy approaching AB along, let's say, curve C1 and fxy approaching L2, another value, as xy approaching AB along another curve C2 where L1 is not equal L2. Okay, so because different value means that it doesn't exist. So limit as xy approaching AB of xy doesn't exist. Okay. So this is then. So one typical question in this section will be the limit. So you need to prove whether the limit exists or not if you approach to some numbers. Well, to solve or to analyze is we need to take some C1 and C2. So we need to make up curves by ourselves. Either the assumption that I think I provide, either y equals 0, x equals 0, y equals x, or even y equals square root of x, y equals x squared, any curves that is simple enough to exchange the equations, and you can solve the equations, and then proving that it has some value as the result. So if you check that C1 and C2 and you prove that, oh, we have different value, which means that limit is not exist. But if it's consistent, like the same value over the time, then we can have the limit. And we are having the limit. The limit exists. So as usual, if we know the limit exists, then the next part is to get the continuity. Okay? So continuity, the same definitions. The limit is equal with its own functions. Okay, so I think let's get through it. So function of two variables is continuous at AB if, take the limit, of fxy is equal to its function at AB. So we say that f is continuous on domain D if f is continuous at every point in the domain. So that's it. So the discontinuity will happen sometimes, maybe be at some limit if we take with different numbers. If the limit doesn't exist, then it will have a discontinuity on that point. I think not much on that continuity, so we can go through the partial derivatives. So this is the partial derivatives. So if z is function of xy, let me just write the definition first. Then the first partial derivatives with respect to x and y are f subscript x and f subscript y, where the fx, this is, we call the partial derivatives with respect to x. This is by definition with limit and the partial derivative with respect to y. The definition, by limit definitions, is taking the y plus h. And provided both of this exist. So how do we see these definitions? So first is we are taking the x as our variable that we respect when we derive, and for f1 we take the y. Okay. So in practice, okay, let me just get you to this quick example. So in practice, if you have a functions, let's say 3x minus x squared y squared plus 2x cubed y. Okay, if you want to know the partial derivative for both x and y, so describe this like partial derivative with respect to x, which means that we're going to derive x as usual. So every variable x we can derive, and for y, since there's not happening anything here, we just treat y as a constant. Okay, so derive this, and taking the 3x become 3, and this x squared become negative 2x. Y squared is just as y squared, just as a constant, and this part is going to be a 6x squared y. Okay, and say this similarly, partial y, because x now is a constant, then when we derive x, it will be 0. Okay, and then this will be negative 2x squared y plus 2x cubed. So in the first one, this is treat y as constant, and here treat x as constant. Okay, so we can write the symbols. We can write the partial x, xy, or just partial x, or with some Leibniz notations. Or we take z as our function, or we can write with the xf. Same way for partial y, we could take that, So in any way you write, I think you can choose which one you prefer. I prefer either the Fy or Fx or the dou F dou X. Okay, any questions? I think I will just up until here for today, and we can continue tomorrow for some examples. Okay. So we are having at least 5 weeks, yeah, 5 weeks before 5 to 6 before your final exam. Okay, so I think we can finish the partial derivative by I think next week. But then we need to have some exercise. And after that, we move to the multiple integrals. I think that one is, in my experience, I think the most difficult one. Okay, if there's no question, then as usual, we are going to have a feedback time.